in residence at California State Polytechnic State University in San Luis Obispo and an adjunct professor of astronomy at Cuesta College.
Okay, thank you, Joe. A little comment on Elliot's talk. We've been working at Cal Poly using high-speed photomultipliers. They have a little more area, not as fast as the SPADs. We were looking into correlators and also into SPADs, and so SPADs are made in Italy, and there's a Canadian firm that distributes these. And so I'm talking to the rep on the Canadian firm explaining what we're looking for. He says, that's really interesting. There was an astronomer back east that just called a few months ago, and then we sold him some equipment. I said, well, can you tell me who it is? Well, he says, well, I'm not really at liberty to do that. And I says, is he from Connecticut? Yeah, right. So kind of the other half of, Elliot talked about using some large telescopes, but of course if we're going to get this to amateurs or we're going to have large arrays of telescopes, then we're going to need to have low-cost telescopes. And the earlier talk that Jean gave on spectroscopy, that was another case where light buckets, perhaps of a little higher quality than might be needed for intensity interferometry. But so you have like a bundle of 440 micron fibers. Yeah, so it's still light bucket territory. Great. I've spent time in astronomy for essentially the last 6 years working on light bucket telescopes and actually building a few. So I was going to just go through that. And so I set up a thing called the Altaz Initiative. We have a website and a Yahoo discussion group. We've had 4 major conferences and over a dozen workshops. The last 2 conferences we held at Canada France Hawaii Telescope on meter class astronomy. And so this got started. I worked on, as mentioned earlier, on robotic telescopes and observatories for a while. And then I moved on to non-equipment parts of astronomy. I was interested in cosmic evolution. And but then the telescope bug bit again. It's kind of like malaria. It's a disease that, it can go into remission, but it never really goes away. And so I spent some time looking around just, before I jumped into something, asking, where is a niche that's not covered now? And I decided that it was really kind of the 1 meter, 2 meter class telescopes. DFM Engineering and the EOS Technologies made those telescopes that they were all, weighed many tons and could cost $1 million up to, a 2 meter up $10 million. And I kind of looked at it and looked at where the technology was and thought that we could do some low-cost Altaz telescopes in that range. So we formed this group. It's quite international. This was our first meeting up in Portland, Oregon at Dan Gray's. He makes telescope control systems as well, control systems for ships. And so that was our first meeting. We had our 6th annual Portland meeting last July. We hold in the end of July. And this was an Altaz telescope that he did, all computer-controlled, robotic. It was a 28-inch one that Howard Banich made. So they were already kind of working away on things. This was a conference we held here in Hawaii, over in Oahu, called Galileo's Legacy in 2009. I see Bob there, and Joe's hanging in there someplace. Yeah, Richard Berry. There was this is Tom Johnson, Kent. So it's kind of the usual suspects, if you will. And so we've had a number of meetings. One of our first projects, I had visited early on. I went around and visited quite a few Altaz telescopes. I wanted to see, how the technology developed. That was one reason I was delighted to have Yuri from the 6 meter. That 6 meter telescope has always interested me. It's a computer-controlled telescope. And one of the first telescopes that I looked at was Magdalena Ridge, the 2.4 meter, which uses one of the better Hubble mirrors. At any rate, they have a direct drive system. The telescope moves very rapidly. They can use it for tracking satellites and so forth. Quiet, no gears, no belts, and everything. So I started wondering if we could build direct drive telescopes for amateur telescopes, and highly precise, and not have all the problems with backlash and everything else. And so I teamed up with David Rowe, and he actually built this first direct drive motor, and then you can see it's here. We plywood, wound the coils, there's magnets, and here's a refined version. It was built at Plane Wave Instruments, and so we put this in. I had Cal Poly students. Here's 3 of the students. It was actually a 7-student team altogether that built the Cal Poly 18 telescope, which had direct drive. So this is kind of the first small amateur class direct drive telescope. And we got lots of contributions. I'm very good at twisting arms, as some of you probably already know, and getting donations and people to help out. And the telescope led to the commercial. This is the Plane Wave Instruments. It's an Altaz 0.7 meter, the CDK 700, and it's a direct descendant from the Cal Poly 18. They're working on a 1 meter version, and of course we keep thinking maybe Plane Wave Instrument will have a 1.5 meter vision. But this is telescopes at lots lower cost than the DFM or EOS technology telescopes. This Richard Berry on the left, he took students, of course, after their senior project is over and they graduate, they are gone. And so, but their projects, even if they're not totally working, remain. And so, at any rate, Richard Berry and Dan Gray adopted the Cal Poly 18 and have continued work on it. And it gives very precise pointing and tracking, and they've added things like an instrument rotator and so forth. So, at any rate, that was one of the early success stories. On to Lightbucket. So this is the definition from Jacqueline Mitten, who wrote the Dictionary for Astronomy. Her husband's an astronomer. And at any rate, so the main idea is it's just a flux on-axis flux collector as opposed to an imaging system. And being on-axis just makes the optical demands a lot easier. And but there's lots of things that it not good to use for. So essentially, the places where a Lightbucket works is where you have a signal noise advantage, and that's where since you have a large area of the sky, since the resolution of the telescope isn't good, it helps if the contribution of the sky background is small. And the other way to put it is, so if you look at bright things, and short integration times helps out there. The aperture helps you, narrow bandwidths, or if you have, like in the infrared, high detector noise, if you have that, then the sky background contribution is small and the Lightbucket works out for you. So here's some of the areas of research. We've been very interested in near IR aperture photometry. Haven't done much on spectroscopy, but I'm certainly hoping with John that we can work in that area. And then intensity interferometry right away is a really nice application. So I read through the Hanbury-Brown papers, and even have a Hanbury-Brown book. This is hard to get. So you've seen that picture. That's his 6.5 meter. Quite nice telescopes for the time. These are really great Lightbuckets. Very nice design. And the key, of course, to lightweight, low-cost telescopes is the mirrors. So our group has spent lots of effort on mirrors. That's kind of probably the main thing besides direct drive. So here's a 1.5 meter meniscus mirror. It's just 3/4 of an inch thick, and it's easily lifted by, as you can see, 3 or 4 people can lift it. The blue is just the plastic coating that we haven't taken off at that point to protect the the aluminized thing. Here's another 1.5 meter mirror still being made by David Davis up in Oregon. So he slumps and grinds mirrors. This is another approach. This approach is taken by Hubble Optics, Tong Lu, in Hong Kong. They actually have their factory optics shop in Beijing. And this is actually the mirror for the Cal Poly 18. It was donated by Tong. And he's gradually worked his way up. It looks like he's going to be able to do 1 meter sandwich mirrors. These essentially 19 millimeter thick 2 plates separated by these spacers. It not only reduces the weight, but it improves the cooling on the mirrors. This is probably the most promising new mirror technology for light buckets. In fact, it looks like it's behind enough quality that it's really better than light buckets. This is Andrew Irigma, and he's down in Florida. And he and I, it's been 5 years now, started thinking about low mirrors originally, plastic mirrors with foam, and then foam glass, made a commercial foam glass, and he eventually ended up making his own ceramic foam. The basic idea is to have lightweight foam between 2 plates of glass to try to match the CTE, and so he's up to 24-inch systems. He's made the 1 meter blank for one of the 1 meter telescopes that we're working on. There's some more pictures of foam. By the way, Elliot, that's Bruce Holenstein in the lower right there. It's very interested in intensity interferometry. Another approach is spin cast epoxy mirrors, and the basic idea is if you spin a liquid at a constant speed, it takes a parabolic shape. It's an epoxy. You just let it harden. You got yourself a parabolic shape. You don't need to do any grinding and polishing and so forth. The problem is the devil's in the details. And but this has been done by engineers before they did it for some of the early infrared telescopes were mirrors. And but Lisa Broadhacker, an organic chemist at Lander University, has been over the last 5-6 years perfecting this technology. We had a 1 meter mirror successfully made for my telescope, and unfortunately, and it has a aluminum substrate. It cold soaked overnight outside when it was real cold, and when they moved it in the lab, the epoxy surface shattered. And this was after. Yes, and Lisa's collaborating with Joe. She's coming over here on her sabbatical. So Joe recognized a good organic chemist when he saw one. So there's Lisa. We're having a workshop, by the way. That will certainly include a little bit on double stars, but we're having a workshop on telescopes and so forth back at Lander University in June. Regular luminizing in vacuum chambers. The vacuum chamber people don't like experimental mirrors usually, and they're clogging up their vacuum chambers. So we've been doing kind of reverted back to silvering. Silvering's advanced a lot since the earlier days. The mirrors are thin and can be flexible, so we've spent with the folks at Gemini and Subaru and other places that use active control mirrors. This is 1 meter mirror that actually one of the IRTF astronomers is working on, Mike Connolly, and we've also had projects on active secondary mirrors. So this isn't AO in the sense that you're trying to get rid of atmospheric distortions at a high frequency. You're just trying to actually shape your secondary mirror at really low frequency to compensate for problems with your primary mirror, your cheap primary mirror. So this was our first telescope, so we didn't want to just talk about it. That's Joe Haberman, who was the chief optician at Celestron, and then Plane Wave Instruments. We're down at their shop. This was the 1 meter mirror. Talked to a friend at an optical company into donating it. It's a spherical meniscus mirror. And here's a 1 meter scope that we developed. The mirror was f4. We didn't have a choice. I would have chosen something much faster, but right there it is. This is Reed and Chris Estrada that helped me build this telescope. And the Tom, you're in one of these pictures here. Oh, here's Tom. And so lots of friends pitched in. This telescope, it's a 1 meter telescope. It loads in the back of my wife's Jeep Cherokee. And it's got a little winch. You have a little ramp you can see, and we winch it up into the back of the Jeep. So it's truly a portable 1 meter telescope. We did some very simple flexing of the mirror to get rid of the worst astigmatism along one axis. So we rotate the mirror around until we found you can see where we got the mirror marked off. And then we could adjust the tension, essentially just warping the mirror into shape. It was a spherical mirror, and we used spherical aberration correction. I went to an eyeglass optician, and you get actual lenses, and use those for spherical aberration correction. This is another, that was a wooden version. We actually took it down to a shop, and they made the measurements, put it on AutoCAD, and had their machinists make up a much fancier version that we call Shiny Sam. And this is, John, this is the one we were talking about. So there it is. And we haven't finished the mirror cell and the superstructure, but the rest of the telescope's pretty well done. And then finally, we decided to try a 1.5 meter telescope. So this is 3 students in architectural engineering. They're very good at designing structures. So they use finite element analysis to design structures. And they usually always do skyscrapers and stuff like that. And when they were challenged to do a telescope, they were shocked when we said, well, we were worried about displacements of millimeters. They're usually working inches for So at any rate, here's a couple of the students and one of the professors. So we built up the model, and we made the model. We do CNC'd out planar trusses to make up the model, and it clicked that we could build the whole telescope that way. And so they decided they wanted to make the telescope out of really top-end plywood. It's called apple ply, and they actually CNC, and you can see them CNCing out and they put the planar trusses together. Apple ply is used usually, and so they entered a contest, and this is the first telescope to win the annual contest. It was $1,000 first prize, which they split. And this is the mirror cell, 27-point flotation mirror cell. Then it has magnetic adjustments. We can adjust on the 6 outer triangles. We can adjust the force. There we're lifting the mirror cell from its packing. That was the unveiling over at Architectural Engineering of the telescope. It has a hexapod truss, truly portable. A little student labor there moving the telescope. And I threw this picture in because we're all here at this conference. And of course, here you couldn't stuff it in the back of a Jeep, so this is me and my neighbor working on a trailer. Here's we fancied the trailer up. This is actually a 1.5 meter dish that we just used for a little solar power experiment. And then we have a 2 meter, so we've been designing a 2 meter version. It's all AutoCAD'd up, and then so these are some AutoCAD pictures. And this is what an idea, maybe an array of portable 2 meter telescopes might look like. And and the last thing, so this is at Cal Poly, and this is Jody Christensen Elliott. And this is one of her students. So we've been working. She's been doing most of the work on intensity interferometry. So we've got 2 high-speed photometers and a correlator. And so what we're planning to do is take the 1 meter and the 1.5 meter telescopes and try changing the baseline and see if that works. Okay, I think that's it.